My name is Frances Pierce. I am a retired geologist. I spent the majority of my career with the U.S. Geological Survey, doing things like energy and minerals and the environment. So today, I'm going to talk to you about the geology of Lake Tahoe. Of the Earth's hundreds of thousands of lakes, most of them are less than 18,000 years old. Lakes form, they fill with sediment, they fill with vegetation, and then they turn into marshes and then meadows. But there are 20 lakes in the world that have held water for longer than 1 million years. And these deep ancient lakes share a common characteristic. They persist due to continued movement along active faults. Such lakes can be extremely deep, and they continue to deepen even as sediments accumulate. Lake Tahoe is one of those deep ancient lakes. So I'm going to start with some facts. And then I will move on to the geology, which includes plate tectonics, physiographic setting, and geology, covering faults, volcanoes, glaciers, McKinney Bay, landslide, and changing lake levels. So first of all, the facts. These you will see in most any newspaper or publication made for people who are visiting the area. Most people are fairly familiar with all of these pieces of information. But Tahoe is the second deepest lake in the United States after Crater Lake. It has only one island, and that is Fannett Island in Emerald Bay. And there are 63 streams that feed water to the lake. And there's only one outlet, and that is the Truckee River in Tahoe City. That outlet is controlled by a dam that was constructed in 1913 to contain an additional 6 feet of water as a reservoir for agricultural interests near Fallon, and to provide water to Pyramid Lake on the Paiute Tribal lands. The natural rim of Lake Tahoe is at 6,223 feet above sea level. The maximum level is 6,229 feet above sea level. And for most of July this year, the pool elevation was just a bit over 6,228 feet, so almost full. Lake Tahoe is known for its clarity. In the 1960s, clarity was about 102 feet. In the 60 or so years since, clarity has decreased to between 60 and 70 feet. This year, the clarity was measured at 80.6 feet, thanks to the decrease in introduced mysis shrimp. The mysis population is expected to rebound, so the clarity will again decrease. In this image, the outline of the lake and its watershed are shown in light blue. The size of the watershed is 505 square miles, and the lake's surface covers 192 square miles. So the lake occupies 40% of its watershed, meaning that 40% of rain and snow that falls directly into the lake without carrying sediments and nutrients from the land. This is one of the reasons Tahoe is so clear. It can be challenging to grasp the scale of geologic time. So I'm going to talk a bit about the geologic time scale. To start with, the Earth is about 4.5 billion years old. At about 4 billion years, tectonic plates formed on the surface, and we'll talk about those more in a minute. At about 3 billion years, tectonic plates started to move around. So we're going to jump over to this column in the yellow and the beige, which represents only 66 million years. And 66 million years ago, the dinosaurs went extinct as a result of the Chicxulub asteroid impact. The basin that holds Lake Tahoe started to form about 3 million years ago, which is this blue star here. Homo sapiens arrived around 350 to 260,000 years ago, which is here. And at the very top of this column is a little skinny place called the Holocene, which represents the last 12,000 years of Earth history. However, another epoch has been proposed, and that would be the Anthropocene. The Anthropocene Working Group argues that industrialization and nuclear age are the best geological markers of this new epoch. They zeroed in on the period of 1940 to 1950 when humans began detonating nuclear bombs, and plutonium is the marker. Rocks around Lake Tahoe are from the Paleozoic here, from the Cretaceous here, and from the Tertiary here. And a little bit of the Quaternary at the top. Another way to think about geologic time is consider it a calendar, a year, 12 months, each month 28 to 31 days, each day 24 hours. And if you think about that time scale, dinosaurs became dominant in mid-December, and they disappeared the day after Christmas. The first human ancestors appeared on the evening of December 31st, and everyone on Earth alive today was born in the last millisecond of New Year's Eve. Lake Tahoe occupies a tectonically active faulted basin east of the Sierra Nevada crest along the California-Nevada border. It's important to understand a bit about plate tectonics and how the tectonic setting is responsible for some of the lake's outstanding features. There are 7 major and about 8 minor plates that cover the Earth. The Pacific plate is one. It's on this image, it's split in 2 on the left and right sides. So the Pacific plate, the North American plate, the South American plate, the African plate, the Eurasian plate, the Australian plate, and the Antarctic plate. Lake Tahoe is shown on the North American plate here where this blue star is. And it was the interaction of the North American plate and the plate that no longer exists, the Farallon plate, that is responsible for the physical features of the Western US, including Lake Tahoe. Tectonic plates comprise the outermost part of the Earth, called the lithosphere. The lithosphere consists of the crust and the upper mantle, shown here, crust and upper mantle. And beneath the lithospheric mantle lies the asthenosphere, here, where high temperature and pressure cause rock to soften and partly melt, becoming semi-molten. Tectonic plates meet and interact in 3 ways. There are divergent boundaries where crust is created, usually at the bottom of the ocean, shown here. Magma comes up, erupts on the surface of the floor of the ocean, and these plates spread apart. At convergent boundaries, oceanic crust, usually oceanic crust, meets continental crust. And because ocean crust is denser, it dives below or subducts below the continental crust, which is lighter and less dense. And then there are transform boundaries. And transform boundaries are places where the plates will move laterally past each other, producing shallow earthquakes, but no volcanic activity or little volcanic activity, and no crust is created or destroyed. So now that you know a little bit about plate tectonics, we're going to look at how tectonics change the landscape over time and influence the type of rocks we find at Lake Tahoe. We're going to start at the oldest period, that would be the Paleozoic era, about 225 to 600 million years ago. Back then, California didn't exist, at least not in any recognizable form. Bits and pieces could be found scattered around in the marine environment off the western edge of North America. And at that time, North America ended in central Utah and Arizona. So this was all probably shallow seas. Other parts of California were probably volcanic islands in the eastern Pacific. And most of what would become California was under the ocean or yet to be created beneath North America. During the Cretaceous, 800 to 80 to 100 million years ago, the Tahoe region, what is now the Tahoe region, was above an active subduction zone. And as the Farallon plate, which you haven't seen yet, but you will in the next slide, which it no longer exists actually on the surface of the Earth, but the Farallon plate started to be subducted beneath the North American continent, and magma rose to form volcanoes on the surface and plutons below. And a pluton is a relatively small intrusive body, which is small, tens of kilometers across maybe, representing one fossilized magma chamber. The magma forming the pluton rises into the Earth's crust, but doesn't erupt onto the surface. So the pluton is down here, volcanoes are up here. The Sierra Nevada batholith comprises more than 100 plutons that are similar in composition and appearance. And a batholith obviously is much larger than individual plutons, up to hundreds of kilometers long and 100 kilometers across. So I call this the satellite view because we've been looking at plate tectonics from an edge-on view. But this is what it would look like from above if you could take a picture in time. Here's the North American plate, Arizona, Utah, Nevada, California. This is a trench where the Farallon plate is being subducted. It's moving this direction, and because it's ocean floor, it's denser, and so it's moving under the continent. This jagged line here is a divergent boundary. It's a spreading center. So new crust is being created here. And the thing to notice is that the Farallon plate is moving northeast, roughly, underneath the North American continent. But the Pacific plate is moving to the northwest. It is not moving toward the North American continent. It's moving relatively away. So in the Tertiary, about 28, 30 million years ago or so, the subduction zone with the Farallon plate here and the spreading center associated with the Farallon plate were subducted beneath North America. And the Farallon plate no longer existed. At about 20 million years ago, the dip of that subducted plate moderated, and melting magma from the subducted plate caused the crust at the surface to stretch and fracture. So it was coming up here, and it formed the Basin and Range province, which we'll look at a little bit more in a slide or two. And it's characterized by north-south trending mountain ranges, linear valleys, and high heat flow. At about 20 million years ago, the San Andreas transform plate boundary was created, formed when the Pacific plate butted up against the North American plate. This slide shows divergent, convergent, and transform margins. And again, it's a satellite view, so we're looking from above. This is the North American plate 30 million years ago. This is the Farallon plate 30 million years ago, moving this direction and being subducted underneath the North American plate in a trench. And the boundary of the Farallon plate with the Pacific plate was very uneven. It's a spreading center. And so 30 million years ago, the Pacific plate hadn't made contact with North America yet. At 20 million years ago, there is no more Farallon plate. It's been divided in two by the part of the Pacific plate that is now in contact with North America. So we have the Juan de Fuca plate north and the Cocos plate to the south. Coming forward another 10 million years ago, we have an even longer boundary between the Pacific plate and the North American plate. And remember, the Pacific plate is moving to the northwest. It's going out this direction. It's not moving underneath or toward the North American continent. They're just sliding past each other in a transform margin. So the Juan de Fuca and the Cocos plates have gotten smaller. And the present day, we go, here is the San Andreas, the transform boundary between North America and the Pacific plate, starts in the Gulf of California and goes up north toward the Mendocino fracture zone, which is here. And for reference, Los Angeles is about here on each of these slides. And on this last slide, San Francisco is here. So the Pacific plate's moving away to the northwest, and the North American plate is about stationary, not completely, but pretty much stationary. So we've come to the present time, as you saw on the last slide. And here, east of the Sierra Nevada, the changes in the plate boundary cause the Basin and Range to form here. So this fossil subduction zone, there's probably a little bit of the Farallon plate down here, and it's melting and rising and breaking up this part of probably Nevada at this point. High heat flow, there's volcanism, and there's faulting. So this is the Basin and Range. It's quite a large area. It starts at the eastern front of the Sierra Nevada and runs for about 500 miles over to the Wasatch Front in Utah. And it's characterized by these north-south trending mountain ranges separated by narrow, dry basins. And as you might imagine, abrupt changes in elevation. This is a function of the melting remnant of the Farallon plate rising and causing the crust to be heated. And then there's also extension going on here. So the continent right here is pulling apart. And that all began about 20 million years ago. The texture in the Basin and Range is characterized as Horst and Graben topography. And Horsts and Grabens, those are German terms. Horsts are these up-thrown blocks, and Grabens are the down-thrown blocks. And this is the kind of structure you get when you pull the crust apart. They're separated by normal faults, and normal faults just mean the hanging wall, this part here, moves down relative to the footwall. So this is a footwall, hanging wall, footwall, hanging wall, footwall, hanging wall. And then these arrows are demonstrating the fact that the crust is extending here. This is a satellite image of the Western US, and it shows the Basin and Range province. The north-south trending basins show up rather dramatically in here, and they're very easy to see. I'm going to talk about the Walker Lane now, and you might ask, why am I telling you about the Walker Lane? And it's because Lake Tahoe lies in the westernmost basin of the northern Walker Lane. So Lake Tahoe is here. Walker Lane is this yellow area, and northern Walker Lane is here. It's a transition zone between the Basin and Range and the east, to the east, and then the portion of California to the west of the Sierra Nevada. This area in yellow accommodates about 20% of the movement between the North American plate and the Pacific plate. So the rate of movement through here is about a half an inch a year, averaged over time. The other 80%, of course, is taken up by the San Andreas Fault, which runs along the western portion of California from the Gulf of California here. This image, on this image, this is Utah here, it's the state line. This is Nevada across here. This is the California-Nevada state line, Tahoe's there. And what you see is that these blue arrows show the direction and magnitude of crustal extension from the Wasatch Front in Utah through most of Nevada. And you can see that the arrows are primarily east-west, not perfectly, but pretty close. But when you get over toward where the Walker Lane is, the direction changes to northwest. So it's a northwest trending zone of right lateral strike slip movement in the Walker Lane. There is some discussion in the geologic community that in some point in the future, probably millions of years from now, the San Andreas Fault, which is this red line here, will step over, which means that it will change where it runs through California. It will go through the Salton Sea where it does now, but then propagate northward toward the Walker Lane through through Death Valley and the Owens Valley and up toward Lake Tahoe. There's not a whole lot of agreement about where it will go when it gets up into this area, but it's not something we'll probably have to worry about. It's just kind of an interesting fact. So now I'm going to move into talking about the rocks. So the Sierra Nevada batholith, which I talked about before, constitutes most of the bounding mountain ranges around Lake Tahoe, the Sierra Nevada on the west and the Carson Range on the east. The batholith is primarily composed of granodiorite, which is a form of granite. It looks like this. It's pretty much black and white rather than maybe pinkish, as true granite is more pink than this. And the granodiorite surrounds about 3/4 of the lake. It starts around Tahoma, about here, comes around the south end and back up the east side toward Mount Rose. There are other rock types in the basin, of course, including volcanic rocks and sedimentary rocks and metamorphic rocks, but primarily we are concerned with the Sierra Nevada batholith. And now we need to talk about faults. In Lake Tahoe, the trough that holds Lake Tahoe that began forming 3 million years ago, the trough is described as an asymmetric half-graben, and I have a picture of that on the next slide. In the image on the left, the authors used LiDAR, and if you have a self-driving car, you might have LiDAR, although not if it's a Tesla. Tesla doesn't use LiDAR. But it's an imaging system, and when it's used for geology, it allows scientists to remove the effect of vegetation and to see only bare earth. So you can imagine, if you looked at the west shore of Lake Tahoe, it's pretty heavily forested, and seeing faults in a forest like that are pretty difficult. But if you can remove the vegetation and just look at the bare earth, then you see the faults. And there was a paper from 2012 that described these series of faults as the Tahoe Sierra frontal fault zone. The image on the right, there are 3 named faults that are labeled here. These are fairly well known, and they start on land and then run into the bottom of the lake. So there's the West Tahoe Dollar Point Fault, the North Tahoe State Line Fault, and the Incline Village Fault. Between Eagle Rock, which is about here, and Emerald Bay, which is here, geologists have measured about 4,500 feet of offset from movement along the Tahoe Sierra frontal fault zone and the West Tahoe Dollar Point Fault. 4,500 feet. The relative movement on both of those faults is down to the east. So it steps down toward the center of the lake. Also between Eagle Rock here and Cave Rock over here on the east shore, wave-cut terraces are 30 meters lower in Cave Rock than wave-cut terraces in Eagle Rock. And those wave-cut terraces are the same age. So that's 30 meters, almost 100 feet of downdrop between Eagle Rock and Cave Rock. Another indication that the movement on the faults is down to the east. And movement along these faults is why Lake Tahoe is one of those 20 lakes older than 1 million years. Even though there's 4,500 feet of offset down to the east between the Tahoe Sierra frontal fault zone and the West Tahoe Dollar Point Fault, the lake is only 1,645 feet deep at its deepest point, which is up about here. And the difference is the sediment that has accumulated on the lake floor in the time since the lake formed. So you've seen a picture that looks like this before, Horst and Grabens. And if Lake Tahoe is an asymmetrical half-graben, what it means is that there's faults only on one side of the lake. In this case, there's several faults, but they are all pretty much on the west, from mid to west side of the lake. And the half-graben means that there's not a matching fault on the other side of the lake. And we're going to move on to earthquakes. This green captures earthquake activity in the Lake Tahoe area between April 7th of this year and June 25th. Most of these earthquakes were magnitude 1 to 4 or so. This large red dot right here covers a series of about 60 earthquakes that occurred between May 14th and June 25th near Peavine Peak, west-northwest of Reno. And I doubt that any of us felt any of these earthquakes because they were so small. But it's not to say that large earthquakes haven't or can't happen in or near the Tahoe Basin, as we see in the next slide. We're going to talk a little bit about earthquakes in the area. The red circle is the area of Lake Tahoe here. By far the largest earthquake on this image is the 1872 Lone Pine earthquake, which had an estimated magnitude between 7.8 to 8.0. And it generated a fault scarp 2 meters tall and shifted the ground about 5 meters to the right. John Muir just happened to be in Yosemite at the time, in a remote cabin, 200 miles from the epicenter. And in his typical poetic exuberance, he ran outside and yelled, "A noble earthquake!" He described the shaking as for a minute or two, the shocks became more and more violent, flashing, horizontal thrusts, mixed with a few twists and battering explosive upheaving jolts. Nature fell silent for a few minutes after the shaking had stopped, but then, Muir observed, suddenly out of the strange silence and strange motion, there came a tremendous roar. The Eagle Rock on the south wall, about a half-mile up Yosemite Valley, gave way, and I saw it falling in thousands of the great boulders. The violent seismic shaking from the 1872 earthquake had set off one of the intensive rock falls, which occasionally happen in the famous Granite Valley. Magnitude 6.0 earthquakes are highlighted in this red circle here around Lake Tahoe, and you can see that they started, well, this map or this image shows them starting in the late 1800s up through, the most recent one was about 1966. These two images, one from 2014 and one from 2018, show earthquake shaking potential in California and California, Nevada. Geologic hazards are naturally occurring phenomena that are capable of causing loss or damage. And an earthquake hazard is anything associated with an earthquake that may affect people's everyday activities. And this includes surface faulting, ground shaking, landslides, liquefaction, tectonic deformation, tsunamis, and seiches. Quite a laundry list. Risk is the potential that exposure to the hazard will lead to negative consequences such as loss of life or economic loss. So a high earthquake hazard does not automatically mean high risk. And also, while you can't change the underlying earthquake hazard, you can mitigate risk by managing the built environment. We also had volcanic activity. This image is of volcanic centers on the west shore of Lake Tahoe. And starting about 2.3 million years ago and continuing to 940,000 years ago, small volcanoes erupted on the west shore from vents located at Eagle Rock here, Tahoe Park Heights, Grand Labakan, and above the Truckee River north and west of Tahoe City. These volcanoes produced lava flows and cinder cones on land, and some lava also flowed into an early Lake Tahoe or proto-Lake Tahoe. Those flows mixed with wet lake sediments and formed subaqueous lava deltas that now mark former shorelines. Subaerial lava flows also dammed the Truckee River 3 times. First at 2.3 million years at Rampart, and the river and the lake level rose about 495 feet. Then about 2.1 million years later, 2.1 million years ago, basaltic lavas dammed the canyon again near Rampart and raised the lake level by 522 feet. And finally, 940,000 years ago, the canyon was dammed a third time by lavas at Thunder Cliffs. This time, the lake level was raised 600 feet above current level. The current and only outlet of Lake Tahoe through the Truckee River Canyon has existed for at least 2.3 million years. The repeated construction and removal by erosion of lava dams reduced erosion and deepening of the Truckee River Canyon that otherwise would have occurred. And poorly cemented lake sediments that form the sill of Lake Tahoe at the Truckee River outlet here in Tahoe City were also protected, which helped maintain the lake's depth. This is a view looking from the lake. Here's modern lake level, that's today's lake level, and looking west up Jack Pine Canyon and at Rocky Ridge. So at 2.1 million years ago, or 2.3 million years ago, I apologize, the first damming of the Truckee River, lake level rose to this red line here. It's been mapped here. And then at 940,000 years ago, lake level rose again, and this is the 600 feet above current lake level. Moving on to glaciers, there are glacial footprints along the west shore of Lake Tahoe. And even though the lake itself never held glaciers, glaciers moved down V-shaped canyons toward the lake, scouring away loose rock and creating broad U-shaped valleys that are now some of the most iconic landmarks, such as Fallen Leaf Lake, Cascade Lake, Emerald Bay, Meeks Bay, General Creek, Blackwood Creek, and Ward Creek. And if you're out on the lake and you're looking back up, for instance, back up Emerald Bay and back up toward Cascade Lake, you see those broad U-shaped valleys at the heads of those lakes. Glaciers act like giant bulldozers. They scrape up rock and soil and incorporate all of that into the ice as they move downhill. And when the glacier's forward movement stalls and the ice begins to melt, the material left behind forms moraines. And the material left at the farthest reach of the glacier is called a terminal moraine. So this is a terminal moraine at the mouth of Emerald Bay. And material dropped as the glacier receded farther are known as recessional moraines. And there are a series of recessional moraines between the outlet of Cascade Lake and Lake Tahoe. And material left at the sides of the glaciers is known as lateral moraines. And so there are lateral moraines which separate Cascade Lake and Emerald Bay from Meeks Bay, and Cascade Lake from Fallen Leaf Lake. This is an aerial view showing Fallen Leaf Lake in the upper left, Cascade Lake in the center, and Emerald Bay to the right of center. And the lateral glacial moraines that flank Emerald Bay wrap around to the mouth here, where they become a terminal moraine. And if you've ever driven your boat into Emerald Bay, you'll know that this is a very shallow entrance to the bay. Highway 89, which runs around this part of Emerald Bay and comes down this ridge between Cascade Lake and Emerald Bay, actually follows the lateral moraine that separates Emerald Bay and Cascade Lake. And the height of this lateral moraine here is the depth of the ice that filled Emerald Bay. We're going to look at another LiDAR image here of Cascade Lake and Emerald Bay. You can see there's no vegetation showing, but it gives you a feeling for the shape of both of those, the bay and the lake. And in the center of Emerald Bay is Fanette Island, which is properly known as a Rauch-Moutonnies. And Rauch-Moutonnies are asymmetric bedrock bumps. So this piece of rock was obviously more resistant than the rock that was excavated around it. And they slope, they gently slope in the up ice direction. So the ice came from this direction, and this is the gentle slope. And then as the ice cascaded over the resistant knob, it started plucking away at the down ice side. And that's what gives it its distinctive shape. There are other glacial footprints along the west shore. There are moraines that flank Meeks Canyon here, and General Creek here. But the parts of the moraines that came out toward the lake were probably removed by the McKinney Bay landslide, which I'll talk about in a second. So you can see these canyons, but you don't see the really good terminal moraine. And in some cases, you don't even see much of the lateral moraines. There was also glacial activity along the Truckee River, and glaciers from the most recent Tahoe and Tioga glaciations flowed down Bear Creek here and Squaw Creek here, damming the Truckee River. And it's postulated that when the ice dammed the river, that lake water behind the dam rose to critical levels. And when it got deep enough, the ice would give way, causing catastrophic flooding downstream this direction. And evidence for this flooding is that there are huge boulders of a rock type along the river in Truckee, so pretty far downstream, Truckee and then on into Reno, that could have only come from Olympic Valley or the Bear Creek drainage. Now we're going to talk about the McKinney Bay landslide. So recent research suggests that a magnitude 7 earthquake along the Tahoe Sierra frontal fault zone triggered the large-scale collapse event from McKinney Bay. This is McKinney Bay here, also here. These are about the same scale, both of these images, just to give you an idea. The earthquake caused nearly 3 cubic miles of the McKinney Bay mega landslide to detach from the west shore of the lake and move 9.3 miles across the lake to the east shore. When it did that, it carried mile-sized blocks. There are a couple of blocks in here that are a mile long and maybe as tall as the Golden Gate Bridge. Samples dredged from the tops of these blocks are poorly cemented lake sediments that resemble the type of rock that underlies the Tahoe City Shelf here and the Sugar Pine Point here. Before that landslide, the shelf was continuous from Dollar Point, roughly, to Sugar Pine Point. Movement of the landslide pushed a wall of water, or a tsunami, estimated to be about 330 feet tall, across the lake from west to east. And when it hit the east shore, it was reflected back to the west as a seiche wave. It's like water sloshing in a bathtub. These waves washed sediment and vegetation into the lake and lowered the lake level by about 33 feet. Waves would have flowed over the outlet at Tahoe City and down the Truckee River. So out and down the Truckee River here. Lake water was mostly muddy for several years after this event. The age of this has been variously discussed over time, and the most recent thing that I found said that it's estimated to be younger than 21,000 years and older than 12,000 years. And that's based on the waves that generated by this slide, washing away 21,000-year-old terminal moraine from the mouth of Emerald Bay. So it has to be younger than 21,000 years. And then samples of sediment recovered from the tops of some of these blocks were dated at 12,000 years. So these blocks have to be older than 12,000 years. And last but not least, there have been fairly large fluctuations in lake level in relatively modern times. And we know this because there are submerged tree stumps found beneath the waters of Lake Tahoe at locations shown on this map and highlighted in yellow, so mostly around the southern half of the lake. And in the top right corner, Here's a photo of a stump that is 7 feet tall and 3.5 feet wide. It's a pretty big tree. Samples from the inner core and outermost portion of another stump indicate that the tree was 350 years old when it died. So, based on the estimated ages of these submerged trees, it's likely that between 5,500 years before present and 4,200 years before present, Lake Tahoe water levels were as much as 12 feet below the current natural rim for a period of between 100 and 350 years. During this time, when lake level was so low, trees were able to take root and grow to their current age. Thank you for listening.